So if you remember that, you will find like annotation clusters, the scores. So just mention which try to get the functions and try to relate the functions with the literature. Right? So what has already been found. You can mention that. Okay, then what else do you need to do? You have to go to pathways and then find out the so this is we have auto transaction here. So you load and this entry. Yeah, so you have some several pathways, right? But now for group 2 you will have if I remember correctly that's SSH, right? And then for group 4 I guess group 1 you have SHH and WNT. So two groups you have these two groups, right? Pathways. So using those pathways you assign the name to that particular group. Okay? So there you have to look at the literature as well. So which so you already know there are 4 groups from the literature. You assign the group name according to what you find in the literature. Right? So if the group is has a high a low score, a low probability score for this pathway, you assign that name to that particular group. Right? So the other groups are 3 and 4. Okay. So that's it for workshop 2. Any questions? Any questions? Okay. Date part is okay? No.
Only the key.
Yeah. So here so you know this is from a medulloblastoma data set, right? And so what you expect is terms that relate to brain function. Okay. Now here, now what's the annotation cluster? Here it relates to vision. Okay, so photoreceptor inner segment, the enrichment score is 13.56. Benjamini adjusted values are these, right? So you take these, so this is vision, this is vision. So we have, yeah, so first 3 groups would be fine. So you take that function and you try to find out what are the functions that have been discovered in the literature and you try to relate them. Okay. So if there is no relation, you can mention that here. So these are the enriched terms. This is what is mentioned in the literature, right? Then what you can do is to the take pathway. Right? Now you look at the pathway that is most enriched. That's here, right? So you click on that. Now this is the pathway, right? The stars mention the upregulated genes, and if you go down, now these are the genes from your list that belong to that path, right? Phototransduction. So what is the outputs from workshop 2? What were the outputs from workshop 2? The G lists, right? G lists from all 4 subgroups. Now here we take 2 data sets. One is the training data set, the other is the testing data set. So training data set is this here .ext2, right? That is where and this is the external data set. So how many samples? How many samples? No.
Focus on the
1,209.
This is external
That's the
testing.
external data. Yeah, this is the data set. Right?
This can you repeat the number?
So for the training data set, so that's 1,500, right? And 1,500 subgenes, 733 samples, right? And the second one, so you can just take a look at that. Okay, so that's 1,494 genes and 331 samples. Right. Then you have to load the genes as well. Okay. So for the input of the SVM, taking the expression values of our DGs are enough, right? Because they will be the inputs for the SVM. Okay, is that logic clear? So what we want, so we have the DEGs from the last workshop. Okay, we take out the expression values for those DEGs and input it into the classifier. Okay, so this is the input for the classifier. Is that clear? Right? Right. So what we do is now we train the classifier. So what is the input into the classifier? The expression values of the DEGs. So what we first did was we had to determine the best cost value. So what is the cost value? That is the parameter, right? So that is the adjusting parameter, the best possible classifier for our data. How do you get the best possible one? That is by adjusting the cost, right? So first you have to determine the cost values. So you give a range. So you give a range and then you just tell the classifier to get out the best value. So when you give that particular range, the best value you get is 0.003, right? But we found out, now if you provide the original range of values that we do, 0.03 lies on the lower end. So it can be something that is even smaller, right? So we try with another range. So we try with another range. Do you understand why we do this step? Because so we want the cost value to be as small as possible. From the original range we took, 0.03 is the best value. It's at the lower end, the lowest end. Right? So it can be something even smaller. So we want to see whether that's the case. So we try with a different range, right? So this is the new range that we are trying with. So let's take out the cost. So what's the cost value? So now you might get a different cost value than what they have mentioned, right? So that's fine. That means there is a difference in the packages that they have used. So what you can do is just go with the value that they have mentioned. So if you run that, okay. So let's go with 0.0048. Where does it lie? Here. Okay. So it's in the middle of the list. So we can go with that. Okay. So if it was somewhere, if it was 3.05, we have to try with another range. An even lower range. Right. So this is the step where you actually train the classifier. Okay. This is the step where you train the classifier. Okay, now what are we going to do? Now we are trying to apply the data set onto our apply the classifier onto our original data set. Okay, so we used the gene expression values of our gene expression values of the DEGs to train the data, to train the classifier. Now we are going to validate the classifier on our original data set, right? So when you run that line, what do you get? The confusion matrix, right? So the confusion matrix. So what does that give you? So the diagonal will give you the number of samples that have been properly classified. Okay. So you can see most of the samples have been properly classified except for one sample. So pretty much this is the actual prediction. These are the no, this is the real predictions. These are the predicted ones. So these are the actual values. These are the predicted values. So one sample has been predicted as 3, right? So one misclassification. Other than that, everything has been properly predicted, right? Then what's the value that you look at? That's the kappa value. Okay. So that's around 0.99, which is extremely good, right? Now, since this is our original data set, right, we have to check for overfitting. we have to see whether our classifier has overfitted to our original data set, because we use that data to build the classifier, right? So to check for overfitting, we need to try with the new data set, that is the external data set. Right, so what we do is we predict it again. So first of all, we have to check the probability values. Okay, so what is the probability value? So if you remember the lecture, for each of the 4 groups, for each sample, so this is sample, the classifier gives a probability value. Okay, so if this is 0.9 and these are some small values, right? So each group gets a probability value. The group that the classifier assigns sample 1 is to group 1 based on the probability value, because it has the highest probability. So what you want is all of the probability values to be high. So if it has assigned a particular sample to a particular group, that probability value has to be high. So we want to check the probability values of the maximum probability values. So it's between 0.8 and 1. That means this classifier is sure of its classifications, right? So if it was somewhere between 0.1 and 0.5, is the classifier good? No, right? So we can't take it. Okay, so now we check for the external data set. So you can check the heat map as well. I'm not going to do that. So it's the same thing. So this is the external data set. What can you say about the probabilities? So the earlier one was 0.8 and between 0.8 and 1. This is between 0.75 and 1. A slight reduction, but that's fine, right? So they have asked that the max probabilities for each sample are a bit lower. Can you think of some reasons why? Right? So you can do a bit of research for that. Okay? So remember, one thing you need to keep in mind is this is an RNA-seq data set. But the training data that we used was from microarrays. Okay, so this is RNA-seq. So you have to remember that. Based on the confusion matrix. So except for a few misclassifications, right? So around 8 samples have been misclassified, but the other samples have been correctly classified, right? So you have to check these. These are the actual labels, these are the predicted labels, right? So based on the actual labels and the confusion matrix, we can give the predicted labels names as well, right? So
Out of 3.
yeah, 1 becomes group 3, right? 4 becomes group 4 becomes group 2, 3 becomes SSH, and 4 becomes WA. Try and see whether 3 and 4 give that pathway as well. Yeah, under David. So under David, the enriched pathway. Check whether it is SHH for group 3 and WND group 4. Right? Yeah, so group 3, when it comes to group 3, right? So group 1, 57 of that of group 3, that is yeah, it falls under
63, right? Totally
57. Yeah, total is
60.
63, right?
Out of 50.
Out of 63, 57 have been assigned to group 1. Right? So 6 of them have been assigned to group 3, but the majority have been assigned to group 1. So that is why you assign that particular label. Right? Check the majority assignments.
Miss, this is the decision data set, right?
Yeah.
And how do we know that the actual group? Since we are testing it now.
Yeah. No, this is what we got from the research paper. Right? These labels we got from the research paper. These are the labels from our classifier. Okay. So now, if this is in group 3 is SHH, you check in David. So you have the David results. You check when the SSH was enriched, the pathway was enriched there. Right? Yeah, so this is where you assign the names to your groups. Right? So it should reflect in the functional annotations as well. So this is the point number. Okay, what's the kappa? That's 0.96. That's a very high value. Okay, so final part.